One of the last topics in Calculus 1 is inverse trig functions. And it may seem like a very esoteric topic, why inverse trig is so important, but it actually becomes a lot clearer when you get to Calculus 2, just how important they truly are. But what we're going to do today is the first thing I'm going to do is actually find the inverse trig functions. We'll start with inverse sine, for example. We know what a sine curve looks like. We should be able to get the inverse sine the way we always get inverses, and that is to reflect the curve across the line y equals x. So let's start with that, and then ultimately we'll be able to figure out the derivative of the inverse sine function. Now we will use the terminology inverse sine and arc sine interchangeably. They really do mean the same function, the same curve. So let's get started by defining what an inverse sine actually is. Now, we know that if we have a particular function, the sine function, for example, and we inquire as to whether or not this curve has an inverse, we would apply the horizontal line test to discover that sine actually fails the horizontal line test. What that means is that that curve should not actually have an inverse function. It fails the horizontal line test. So how is it that we do have an inverse sine function even though it fails the horizontal line test? And in fact, if you were to reflect that curve across the line y equals x, what you would find is a curve that alternates back and forth along the y-axis. Instead of going left to right, it goes up and down, therefore failing the vertical line test. So the new curve would not be a function. So to get around this, what we did was we selected a portion of the sine curve, just a piece of it, that does pass the horizontal line test. You'll notice that this portion does pass the horizontal line test, and we'll actually begin the graph here and terminate the graph there and literally delete most of our sine curve. So we have what's called the restricted domain version or the restricted sine curve. Now, once you have the restricted sine curve, we're going to create the inverse by reflecting it across the line y equals x. But before we do so, I'd like to establish what the domain and range is at this very moment for sine. So right now, here's my domain and range. My domain is only from minus pi over 2 to pi over 2. Domain is for x. My range is the standard range for sine, which goes up to 1 and down to minus 1. So maybe I can label that up here. This is positive 1, and I can label this down here as negative 1. So our domain and range, normal domain for a sine curve is all real numbers. We have restricted that domain just between minus pi over 2 and pi over 2. Now the next step is let's find the inverse sine curve. And here's how we do that. To find the inverse sine curve, we take the original portion of the sine only between minus pi over 2 and pi over 2, and we reflect it across the line y equals x. So here is the original piece of the sine curve. Sorry, right here. There's the original piece of the sine curve. You see it? It's got the same shape as it did before, peaking up at 1 and then dipping down to minus 1, only between minus pi over 2 and pi over 2. And I reflected it across the line y equals x. Now remember the reversal of variables when this happens. Y's become x's. So let's talk about what happened to the domain and the range of this brand new curve. This guy right here that's got, instead of curling upward here, it curves downward. This is called the arc sine, or the inverse sine. What is our new domain and our new range? Well, it all has to do with the variables being swapped. So instead of y going from 1 to minus 1 here, instead of a y, we put an x in. Well, x means domain. So our new domain is from negative 1 to 1. Instead of an x being in this inequality, the variables get swapped and we get a y. A y means range, so now the range is from minus pi over 2 to positive pi over 2. Well, that clearly indicates that the inverse sine or arc sine curve can only accept input from minus 1 to positive 1. Anything outside of that domain doesn't give me an answer. In fact, you can see it on the curve right here. Here's -1, and here's +1, and you'll notice that the inverse sine curve really does begin at -1, and it really does end at +1. And if you were to use the function beyond that, you won't get any results. So let's actually use the arcsine or inverse sine curve. What is the arcsine of a half? Arcsine translates into the following English sentence. What angle would you what angle would you take the sine of to get 1/2? I'm thinking logarithms, I guess. What angle would you take the sine of that yields 1/2? Think about that for a second. You would take the sine of the sine of 30 degrees, right? So the sine of 30 degrees is what gets you the half. Therefore, the answer is 30 degrees, but in radians, that would be pi/6. So the answer, the y output, is actually an angle. So the y values are angles, which makes a little bit of sense now that you know that the y value output is from -90 to 90 because they are actually angles. Let's try another one. What's the arcsine of 1? What angle would you take the sine of that gets you a y value of 1? Well, I think you know the answer to that. You take the sine of 90 degrees. The answer, therefore, is pi/2. So we've seen how we develop the arcsine curve. We've run a couple of examples. I have one more example I'd like you to try, and that's this one. This one is the arcsine of the number 2. So let me put this out here, and I want you to think about that one for a moment. So this is the arcsine of 2. What angle would you take the sine of to get 2 on your sine curve? What angle would you take the sine of? There is no angle you can take the sine of that would get you a 2. That answer is undefined. Now, it's best to visualize that. In fact, here is a sine curve right here. Take a look at it. And here's that sine curve bouncing back and forth between 1 and -1. And the angles would be here, the x's. And there is no angle that ever reaches up to y value 2. So there we have it again. The domain is from -1 to 1. If you fall outside that domain, you do not get an answer. Arcsine of 2 is undefined for that reason. So arcsine, arccosine, they all provide angles. Those are the outputs. Okay. Now, next thing I'd like to look at is cosine. Y equals cosine x. And if you look at the cosine curve, you'll notice that if I were to draw horizontal lines, we would again fail the horizontal line test. So it was decided that we would select a portion of the curve, and that portion should satisfy the horizontal line test. Now, I do not think selecting pi/2 to -pi/2 is a great idea because it will still fail the horizontal line test. In fact, the best choice is from 0 to pi. So we choose from 0 to pi to be our restricted domain on our cosine curve. So that's our new domain, whereas the old domain was all real numbers. We've actually restricted it to this window and this window only. Now the range on the cosine curve is basically the same as the range of the sine curve. Right now the range is from -1 to 1. Those are the y values being produced. And if we were to create the inverse cosine or arccosine function, remember there's that reversal of variables, so x's become y's and y's become x's. Domains become ranges and ranges become domains, so therefore on the arccosine curve, the domain, just like the arcsine curve, is from -1 to 1, but the range is different. The output will be from 0 to pi. And you could try this on your calculator. If you do arccosine of any number, well, of course, any number in this domain, you only get answers from 0 to 180 because your calculator may be set in degrees, and it will give you the answer in degrees. If it's set in radians, it'll be between 0 and pi, which is 3.14. So there's our domain and range for the arccosine curve. Now, this is a course in calculus, so naturally the thing that's concerning us the most on this brand new curve that we've developed, and we'll stick with arcsine. It's a good example. Here it is what is the slope of the tangent line? And that's something that calculus can help us with. So this is a curve like any other curve. This is a curve. It's not the sine curve. It's actually the curve goes the other way. It almost looks like an x cubed curve in some ways, but I don't think it'll fit x cubed perfectly. But it is a curve. It's an inverse trig function, and that curve, like every other smooth curve, has a slope. So that would be my question. What is the slope? Now you know how to get slope of a tangent line, and that is to use the derivative as a tool to do so. So what we need right now, the derivative of arcsine. I'm not going to look it up. We could certainly look it up in the book, open up the book, go to this section, and it'll say right in there what it is. But if we do that, we won't really have the insight as to how they figured that out and why it's so different than what you think it might be. If I didn't know any better, I would say the derivative of arcsine is arccosine. That would be a very good guess. But actually, it's much different than that. So let's see if we can figure out what the derivative of arcsine is. So here we have our function, y equals arcsine x, this new function up here. Here is what we're looking for, dy dx. So there's another version of arcsine. It's called the inverse sine. They're the same function, just different name. And what happens when you take an inverse function and you move it across the equal sign? It actually would come over here, and it would become the original function. Well, that's actually rather convenient for us, and here's why. Because when I move it over, I now get a new equation, sine of y equals x. Now, notice that I did not reverse the x's and y's, so I'm really talking about the same function. I'm not talking about the inverse of this arcsine curve. I'm talking about the same arcsine curve. I did not swap x's and y's. I did move this, which I'm allowed to do, and it came over. So it now says sine of y equals x. So the dy dx that we want up here is actually the same dy dx down here. So I think we're in better shape now because I think we can find dy dx. But wait, what is the sine of y equal x actually mean? Well, first thing I noticed is it says the sine of y, so as I said before, y is an angle. Now we know that. We take the sine of angles. But x can be written as x over 1, and I think we all remember what the sine definition is. Sine is opposite over hypotenuse. So a good thing to do at this point would be to draw a triangle that contains that angle y, and let's label the opposite and hypotenuse sides accordingly. So here's a nice triangle where you have your angle y. It is an angle. This says that opposite side should be x, the hypotenuse side should be 1, and side A is unknown at this moment. But we certainly know how to get side A, right? Pythagoras said that a squared plus b squared has got to be c squared on a right triangle. It's been proven many times over that it is correct on a right triangle. So that gives me the means of finding side A. Next step here would be to take the square root of both sides, but we only want the positive version because A is a measurement. It's a positive measurement. So we've got side A. We've got side A. Now I'm going to save this triangle for later. It's going to come in handy in just a little bit. Let's get back to the real problem at hand, and that's this. So let's save that for later. So the arc sine, or inverse sine, is my function. I moved the inverse sine over. It became sine. It's still the same curve, by the way. This would draw the same curve as that. Here's our prize. What is dy dx on this curve? That is the question after all. You'll recall from implicit differentiation that you can do whatever you want to an equation as long as you do it to both sides. Now, if you're looking for a derivative, what are you going to do to both sides? You're going to hit both sides with the verb ddx. So let's ddx the left side and also ddx the right side. Now, when you ddx the left side, what happens? Well, you see I'm working through my chain rule here very carefully, so the first thing I'm going to do is, of course, take the derivative of sine, which is cosine. No change to that argument. Next, I'm going to reach inside and check off my y and do what I'm supposed to do with chain rule, which is ddx the letter y. That's exactly what we've been looking for, dy dx. That's the prize. Now over here, ddx of the letter x, that's pretty easy. That's just 1, so I'm not too worried about that. That's just 1. Well, this is the prize here. We need to solve for it. dy dx is actually what I'm most interested in, so let's get rid of that cosine and divide both sides by cosine. So I think we have found our result. Our result is that dy dx is 1 over the cosine of y. Now, I want to talk to you about what I don't like about that result. When we take derivatives, we like to find new functions. The derivative is a function. Generally, we like it to be a function of x if we can do that. This is not. This is a function of y. So can we fix that at the end? And that's an important step. And I think the way to do it is to go back to the triangle. Now, I realize that some people are saying, can't you just call that secant of y? Yes, you can definitely call it secant of y. That's okay, too. But you still got a y. Now, it says 1 over cosine of y, y meaning the same y up here, the same y up here, y being this angle that lives inside this triangle here. So why don't we just simply do the cosine of y on that triangle? So that's what we're going to do. The cosine of y is adjacent over hypotenuse. Adjacent being that side right there, hypotenuse being 1. Adjacent over hypotenuse is square root of 1 minus x squared over 1, or just square root of 1 minus x squared. And we have translated our y back into x's, and that's good. But don't forget the final answer. The final answer is dy dx is 1 over that, 1 over cosine. So let's write that down as our final answer. And we've got it. So if I had just given that to you, you'd probably say, where did that come from? You know, it makes no sense. The derivative of an arc sine should be some other trig function. This is actually a trig function. It's not a trig function in the sense of sine and cosine, or arc sine or arc cosine, but take a close look at what's in here. This piece does come from trigonometry. That piece right there comes from the Pythagorean theorem. So there is a piece of trigonometry in it, but isn't it interesting that it does not have an actual trig function like sine, cosine, tangent, or the arc sine, arc cosine, arc tangent? It actually looks like an algebraic fraction. Now, we could derive the rest. We don't have time to do that, so I will show you all of them. The derivative of arc sine is that. We just figured that out. If you went through the same process that we just went through for arc sine, but you did it for cosine, arc cosine, it's not all that different, but it is negative 1 over the square root of 1 minus x squared. And if you did it for arc tangent, you get something very different. You get 1 over 1 plus x squared, which is a pretty clean-looking fraction, actually. No square roots or anything involved. And let me describe to you why there are no square roots here. If you were to derive this one the way we derived arc sine, you would have inverse tangent, arctan. You'd move the tangent to the other side where it would become tangent, and then you would take your derivative. Now, think about what the derivative of tangent is. The derivative of tangent is secant squared. So while you might go to the triangle, and you will pick up that square root at some point, but then it goes into squared. Square root squared, cancel. That's why there is no square root here, and it's primarily because the derivative of tangent secant squared. Let's try a few of these. What's the most important rule that you need to remember? Chain rule. Chain rule gets overlooked often. So let's make sure that we not only run the derivative for these inverse trig functions, that we also run the chain rule at the end. So let's start with this one. The derivative of arc sine of x squared. Now, I guess I have to be careful here. because the answer is not always that. This is just arcsine of x. The real answer is 1 over the square root of 1 minus argument squared, not just x, argument. So how would this one work? The derivative of arcsine is 1 over the square root of 1 minus argument squared, because that's the pattern for arcsine. Here it is again, 1 over the square root of 1 minus argument squared. Now, I'm hiding a derivative over here because we didn't forget our chain rule. The derivative of x squared is just 2x. And so the overall derivative here would be a fraction. And here it is, 2x over the square root of 1 minus x to the 4th. So why don't we look at the rules as they would be written in the book, in the derivative tables. Here they are. So it is truly 1 over the square root of 1 minus argument squared. And what's this u prime doing here? Well, this is the same thing u prime is doing on every single derivative that you will find in a derivative table. It's a reminder. It's the chain rule. Okay, so don't forget your chain rule. U prime should always be there. So here they are. So it's not really x squared here, here, and here. It's actually argument squared. So make sure you use the full and complete argument in there. Let's try another derivative. Let's try this one. What is the derivative of the arctan of the square root of x? It might be nice to have our derivative table handy, primarily the arctan derivative, just in case we forgot it. All right, so the derivative of arctan is 1 over 1 plus argument squared. Let's start with that. 1 over 1 plus argument squared. So there it is. My argument is the square root of x. What about u prime, guys? U prime says the derivative reaches in and takes the derivative of that. You know what we call that? The chain rule. So I'm not quite done with this problem. But I do like what happened to the initial fraction. What happened to the initial fraction was it cleaned up very nicely, because that's just 1 over 1 plus x. We still haven't taken this derivative. We still have calculus to do, but we do calculus on exponents, not radicals. So now let's go ahead and take our derivative. The 1/2 drops down. Deduct 1 from the exponent. Let's do that carefully. What do we got? Well, it's time to clean things up a little bit. Now, the 2 resides in the denominator. The 1 plus x resides in the denominator. Even this resides in the denominator because it's a negative exponent. Let's put it down where it really belongs. It belongs down below, and it is a 1/2 power, so it's actually a square root. So let's put it down there where it belongs. There it is, right down below. Now, if we can avoid leaving a radical in the denominator, I do want you to eliminate that radical, and the way to do that is rationalize the denominator. Now, if you multiply it top and bottom by square root of x, you get a square root of x on top. You get a 2. These go together to make a letter x on the bottom, and a nice clean x plus 1. And in fact, there now are no radicals in the denominator. So that's how we take the derivative of an inverse trig function. Number one, you need to know the derivatives of the inverse trig functions. And if you forget them, they're in the book. They're in the derivative table at the very beginning of the book, and they will definitely be available to you on the final exam, for example, on a formula sheet. So it's nice to know how to use them, but if you forget them, you can look them up. And again, don't forget your chain rule. That's really important. Okay, let's continue. I want to try another derivative, this time an arc cosine. So what is the derivative of the arc cosine of e to the 2x? Not the cosine of e to the 2x, the arc cosine of e to the 2x. Now, in order to do this, you start with your outer function first, like we always do, and we run our chain rule. So first thing is, I got to look up the derivative of our cosine, or at least remember what it is. The derivative of our cosine is negative 1 over the square root of 1 minus argument squared. So let's write that down. Negative 1 over the square root of 1 minus argument squared. Next, reach inside and take the derivative of e to the 2x itself. E for easy. So the derivative of e to something, well, I haven't actually done it yet. So that's just something we're going to need to do. So this is chain rule. Don't forget to take the derivative of the argument as well. So what do we got so far? Well, right now, over here, remember, when exponents are in a diagonal line, they actually multiply. So 2x squared would be times 2, actually, or 4x. And that's a good way to clean that one up. All right, let's take the derivative here. Let's do our chain rule. The derivative of e raised to that variable power, luckily, just is e raised to that variable power, e for easy. But the derivative of 2x is 2. That's a chain rule that we can't forget. So this stuff is really on top, belongs on top. And so in the end, we would write our answer as such. Minus 2 e to the 2x over the square root of 1 minus e to the 4x. Okay. Now, let's take a look at a few homework questions. Problem 54. Problem 54 is a mixture of a bunch of different functions. Look at this. X times arctan of 2x minus a quarter, natural log of 1 plus 4x squared. Completely different functions, completely different arguments, and yet there's a hidden surprise in this problem. So we won't know that surprise until we actually go ahead and take the derivative. But the first thing that I noticed was right there. X times arctan. That would be a product rule, and we can't forget our product rule. So let's do a product rule first. Now, the f and the g part is simple, isn't it? You just copy. So f is equal to x, g equals that function arctan. We'll deal with this one later. Now let's do our derivatives. The calculus aspect, f prime. F prime's pretty simple, right? F prime is just 1. Got that out of the way. And now, arctan all by itself. What is the derivative of arctan? Well, you can look it up. It's right here on our formula sheet here. What is the derivative of arctan? It is 1 over 1 plus argument squared. Of course, times u prime, because that would be just a reminder of the chain rule. So let's actually do that. 1 over 1 plus argument squared. 1 over 1 plus argument squared. There it is. Chain rule says derivative of 2x, which is just 2. So that 2 does belong on top. Okay. So let's do our product rule. F prime g plus fg prime. Let's see what we get out of that. Let's start with f prime g. So f prime g is 1 times g. That's be arctan of 2x. That's all you get. Fg prime would be f times g prime. Well, that's 2 on top times my x. And then 1 plus 4x squared in the bottom. So that's just your product rule right there. That's your product rule. All right, so we took care of the product, and we have a derivative. Now we need to work on this guy right here. Now the derivative of the quarter there, the minus 1 quarter, you know what's going on there. It's a constant multiplier. We're not doing anything. It's along for the ride. But what's the derivative of the natural log? Well, the derivative of the natural log is very well known to us. It is 1 over argument. Okay, 1 over argument. I want to cover this up for a second because I'm not ready for it yet. 1 over argument. Argument is 1 plus 4x squared. 1 over 1 plus 4x squared times the derivative of this guy, 4x squared, which is 8x. That would be your chain rule. Let's not forget our chain rule. Now here comes the hidden surprise. Who would have thought this would happen? Look at that. They're the same thing. Now what happens when the denominators are the same? You get to add straight across the top. But what is across the top? There's a 2x here. The 8 and the 4 cancel. That's a minus 2x on top. Well, 2x minus 2x is 0. So there's the hidden surprise. Those two fractions completely canceled each other out. And that came as a big surprise, actually, totally unexpected. So what is y prime? That's it, arctan of 2x. Pretty amazing how that one ended up, that the two fractions not only shared the same denominator, but they shared the same numerator. I'm sure that was a setup. So yeah, we want to carefully take our derivative of our inverse trig functions. We don't want to forget the derivative of things like natural log. And this is just what seemed to happen here. The chain rule also was used, and the fractions were an exact match. So it's an interesting result, definitely. That's problem 54. Let's take a look at another aspect of the inverse trig function, one that does not require calculus. Problem 25. Problem 25 says, can you calculate the cosine of the arcsine of 2x, and can you do it without using a trig function? So we're not supposed to use sine, cosine, tangent, arcsine, arccosine, tangent, none of our trig functions. Can I rewrite that using just an algebraic expression? And the answer is yes, we can, and here's how we do that. What we're going to do here is, when we take a cosine, don't we always take the cosine of an angle, correct? So what I want you to do is label the argument as an angle, theta. So we will later take the cosine of theta. But for now, pull the theta out and tell me what it's worth. Well, theta is the entire argument, which is the arcsine of 2x. Another way to write arcsine is inverse sine. Move the inverse sine to the other side like we did in the previous problem, and you're going to get that the sine of this angle theta is just 2x. So let's write that down. Sine of theta is just 2x. But I think there's a little more to that, because we also know that sine is opposite over hypotenuse. So now we have a theta that would live inside of a right triangle, and we have an understanding as to what we would label the opposite side and what we would label the hypotenuse side. Very similar to before. So let's go ahead and do that. Here it is, the right triangle with an angle theta living inside, with an opposite side of 2x as called for, with a hypotenuse side as 1, called for here, and then we just don't know side A, but we know how to get side A. That would be the Pythagorean theorem. A squared plus B squared is equal to C squared. So A squared plus 2x all squared, and if you do that, you're going to get 4x squared is equal to 1. I would move the 4x squared to the other side, where you get a squared is 1 minus 4x squared. And finally, let's get a by taking the square root of both sides. But naturally, we take just the positive version. And the reason for that is because a is a measurement. It is the measurement of a side of a triangle. This is the way we deal with functions that are mixed together. When you mix a regular function and an inverse trig function, theta equals the inside. Move that function over so we do have an original trig function back. Put your theta in your triangle, put whatever sides are called for based on the trig function, find the missing side with Pythagorean theorem. And finally, let's not forget the actual problem. We have to roll back here to see what it was. The original problem says, can you just get me the cosine of theta? And the answer is, of course I can, because here's my theta, and I know what the cosine is. The cosine is simply adjacent over hypotenuse on that particular triangle. So the answer at the very end is, what is the cosine of theta? Well, it's just adjacent over hypotenuse. Adjacent meaning that side, and hypotenuse meaning that side. So it's that square root over 1, or just that square root. So that's how you figure out how to solve this particular problem when you have a regular trig function and an inverse trig function mixed together. No calculus required. The triangle is definitely required. Okay, one last problem. Again, not calculus necessarily, but it is solving an inverse trig equation is what it really is. This is what we've got here. The arcsine of 3x minus pi somehow is equal to a half. Now, I'm much more comfortable with sines than I am arcsines. So we're going to change this arcsine to what it also can be called, which These inverse signs, they're synonymous. Bring the sign to the other side, please, and that becomes a regular sign. And we're certainly much happier about that. So if you bring the inverse sign to the other side, it actually becomes a sine, just like that. Now, technically, how do you do that? Because I keep talking about moving functions from one side to the other, and they change from their regular to their inverse counterparts. Well, here's the behind-the-scenes work that's going on. I'm actually starting with this equation, and then I take the sine of both sides is really what I'm doing, because you can do anything you want to an equation as long as you do it to both sides. But look what happened over here. When a sine touches an inverse sine, when any time a function touches an inverse function, they cancel out, and you get what's inside. So it's just as easy to move this over and call it sine over there. So what do I have right now? I have that the sine of a half is equal to 3x minus pi. There's my prize, right out in the open. So next step, add pi to both sides. So I added pi to both sides, and I get that 3x is equal to pi plus the sine of a half. It's tricky, though, because it says the sine of a half. I'm a little confused. If it said the inverse sine of a half, I can actually solve that. Inverse sine of a half, what angle would I take the sine of to get a half? That's 30 degrees. I actually have an answer for that, pi over 6. But it actually says the sine of a half, so I would leave it just as you see it. That's the sine of a half a radian. Divide both sides by 3, and we can reach our conclusion. X equals pi over 3 plus whatever the sine of a half a radian is divided by 3. Now, I did run that through my calculator, and when no units are mentioned, it does default to radians in mathematics, so I used radians in there, and I got about 1.207. So I guess you would check it, and the way you would check it is by doing this. Is it really true that the arc sine of all this stuff in here, with 1.207 roughly, is that really a half? And that naturally would be a way to check your answer. So I'm going to switch my calculator into radians, and I'm going to try it. Arc sine of that number. So I've got an iPhone calculator here out. So I'm going to first of all calculate 3 times 1.207. I'm going to subtract pi, and I'm going to do the arc sine of that. Second function, there's my inverse sine right there, and look at the answer, 0.4999. It really is a half. We got it. So that would be the result. So I encourage you to work on some of the homework problems. Definitely do the calculus for these derivatives. You know, take the derivative, know what the derivatives are, and don't forget your chain rule. Thanks.